Okay, let me give you guys some more examples of proportionality. So I looked on the internet that the volume of the sphere is given by this. Now let's say you're a manufacturer of chocolate sweets. You're trying to create spherical chocolate balls to sell. Now you can see that the volume of the sphere really represents the amount of chocolate that you would need in order to create that sphere. Now we want to investigate what we want to investigate the amount of chocolate needed as you vary the radius of the bulb. So currently your company is undecided on the size of the sphere. So it could be a big spherical ball, or it could be a small spherical chocolate sweet in your case. Okay. So what happens to the amount of chocolate needed as we change the radius of the sphere? Okay, so let's look at this here. At the moment you've got a fraction multiplying let's multiplying this bubble here. So when you multiply a fraction, it gets multiplied to the top. So it then becomes this 4 pi r to the power 3 over 3. Okay. So now visualize it like this. Here you've got a bubble here multiplying with this bubble here. Let's move this 3 to the power. Sorry, let's move this r to the power 3 out. So it looks like this: 4 pi over 3 r to the power 3. Because here you've just got a fraction multiplying another thing here. So when you multiply it, it goes to the top. So you're all allowed to do that. You're all allowed to take it out here. Now here's the thing. So currently v equals this. Now you can actually say this. Remember, v represents the amount of chocolate we will need in order to create the sweet. So we could say that the amount of chocolate needed is equal to this thing here. But the thing is, I'm going to call this K, this new bubble here, K. So really I've got this here. What I'm trying to say is that this bubble here I'm going to call everything inside this bubble a new number, K. What I'm trying to say is that, you see, 4 is just a number, it doesn't change. Pi is just another number, it doesn't change. 3 is just another number, it doesn't change. And we don't care what this thing is, just a constant. It's just a number that doesn't change, and it's a number that we don't really care about. So let's just call it a new name. Let's just give it a new name, K. And K is another. It's actually the same number, but we don't care about what this number really represents. We just care that it's a number that doesn't change. So let's call this whole complicated thing a neat K. Okay, so this new number, well, it is the same thing, but it just has a different name, K. Okay, so here the amount of chocolate needed is, well, here when you've got chocolate equals K to the power K times r to the power 3, you can actually say the amount of chocolate needed is proportional to the cube of the radius. Okay, so you can actually make this statement here: the amount of chocolate needed is proportional to the cube of the radius. Because once the minute the minute I make this statement here, you could inside your mind immediately jump to chocolate needed equals a constant to the power 3. That's like going back to here. So when we are here, we can make this statement: chocolate is proportional to the cube of the radius. Okay, so going back to here, going back to here, we can say that the amount of chocolate needed is equal to a constant to times the cube of the radius. Now let's investigate that. Let's investigate what happens when we double the radius. So our sphere is really big. What impact will that have on the amount of chocolate we would need? Okay, so this here, this here represents our old radius here. It's just one radius here. Now let's investigate what happens when our new sphere has a radius of 2r. Okay, so let's put this 2r. So currently you've got this thing here. Remember, you can visualize it like this, to the power 3, and this thing here exists in a bigger bubble here. Okay, so now so this is our old sphere. Now our new sphere, let's call it a new sphere here. The amount of chocolate needed for our new sphere. Remember, our new sphere has a radius of 2r. So now put this 2r into this bubble here, into the r here. Okay, so our new radius will be that same number, which we don't care about. Well, remember, it's like this. We put this. Our new radius is 2r, so we can put it into this thing here. Okay, so now, well, really, this is a bubble within a bubble here. Okay, so look what happens now. So when you get 2r times 2r times 2r, because that's what's happening here. You're cubing it. Now number times with a number times with this number here, that will give you 8. Hang on, k here, and that will give you 8. So this is in a bubble here, and we've got a bubble here, and this is in a bubble here, and we've got a cube here. So basically, this thing here. Oh wait there. Sorry. This then becomes, hang on, because we are using the to the power of 3 here, and we are using the 3 to act on this 2r. So then this then becomes 8r to the power. Oh, hang on, 8r to the power of r to the power of 3, because 2 times 2 times 2, that's 8, and then you've got r times r times r. So this here, this is our new, this is the amount of chocolate needed for our new sphere. Okay, look at this here. Our old sphere, we require a number that we don't care about, r to the power of 3. But then look at this here. We now have an 8 in there. So let's just move the 8 to the front. Look what happens now. Hang on. So here's 8, and then k r to the power 3. I'm just moving the 8 out. So now here, you see, this thing here is our old sphere. You see, can you see that? It's exactly the same, k r to the power 3. But then our new sphere has an 8 in front of it. So what that means is that the amount of chocolate needed will be 8 times as much. You see, this bit here is our old amount, but now we've got 8. Well, the amount of chocolate equals 8 times as much. So when you double the radius, you will actually need 8 times as much chocolate in order to create that sphere. Now look what happens when you half this. Okay, so now the radius is half r. Half r, or r over 2. Let's use r over 2. So now we look what happens when you half the radius. So remember, hang on, the amount, well, it's just a constant times r to the power of 3. Now if we put, so now it's just a bubble here. So this here exists like this. Okay. So now hang on, this is r over 2. Look what happens when we put r over 2 into this thing here. Okay, hang on, this is ugly. Hang on, let me do it again. So here the volume is some constant r to the power of 3. Okay, so now we are putting, well, we want to investigate what happens when we half the radius. So put this thing here into the r here. Okay, into the r here. So it will become this, a constant r over 2 to the power of 3. Okay, then this will become k r to the power of 3 over 2 times 2 times 2 over 8. Okay, so now hang on, let's just rearrange this. So this then, here you've got a k multiplying a fraction, so it gets multiplied to the top. So it will become k r to the power 3 over 8. Okay. So now I'm gonna do this. I'm gonna take well, I'm gonna visualize it like this. 1/8 times k r to the power 3. Okay. So really, you've got a bubble. So when you times a fraction, it gets multiplied to the top. So it will give you this, which does make sense. Okay. So here, this is the volume of our new sphere. Remember, our new sphere now is a small sphere. It has a radius. It has half of the radius. Now, if you look at this here, our old sphere is just simply k r to the power 3. But our new sphere, and well, remember this here represents our old sphere. It's exactly the same, k r to the power 3. But then our new sphere has 1/8. You see, the amount of chocolate needed now, you've got this divide by 8 thing here. So what that means is the amount of chocolate needed will be, well, get your old one divided by 8. So it's a pretty much what it's trying to say is that the the amount of chocolate you would need will be 8 times less than the normal amount. So when you double the radius, you will need 8 times more amount of chocolate. When you halve the radius, you will need 8 times less the amount of chocolate. Okay.